Thanks for joining me. And today I'll be talking about using machine learning models to predict underwriting decisions for life and health insurance. Let's start with a joke. Underwriters reject everyone, am I right? If there are any underwriters sitting in the audience, I hope you have a good sense of humor. Clearly, this is a common misconception, but the public sentiments about insurance underwriting remain pessimistic. And insurance underwriting is often cited as one of the major barriers to entry, especially for underserved population. One of the common complaints about insurance underwriting is that it's lengthy, costly, and often end up in rejections anyway. So the aim of the presentation today is to improve the current underwriting process, more specifically, achieve high prediction accuracies, so the percentage of applications that can be accepted straight away is maximized. Second, classify applications into different risk classes, so if the insurers want to concentrate on certain risk classes, they can do so. The usefulness of this point will become more apparent in the presentation later. Lastly, provide underwriting insights. So one of the first questions that I received when I started this project is, how do machine learning models differ from the current existing underwriting automation tools? Hopefully, this flowchart of the underwriting process will provide answer. Applications are first processed by some sort of rule-based system. Currently, a lot of the improvements in automation have been concentrating on encoding more and more underwriting rules into those engines. So essentially, these engines act like cookie cutters. That is, if a case doesn't fall into a specific underwriting box, it will get thrown out by the rule-based engine, and underwriters will be called upon to review the case. Sometimes underwriters can make decisions on these cases, but often they're referred to reinsurers due to referral limit or complicated or rare medical conditions, which is usually why they're thrown out in the first place. So part of the red box represents part of the process that is costly and lengthy, and this is potentially the area that insurers want to improve efficiency. The data set used for training machine learning model for this presentation is represented by the gold box. That is, it is referred cases only, which means the data is skewed towards more complicated cases with larger average sum insured. So back to the question. One cannot compare the accuracy score of the current automation tool or the rule-based system against the accuracy of machine learning models, because the machine learning models for this presentation are designed, or by definition, to handle the cases that cannot be handled by the current rule-based system. This diagram here shows the steps that I took to train machine learning models. The first step is to use natural language processor to process the text variables in the data, including the descriptions of medical conditions, the family history of medical conditions, risk lifestyle factors such as alcoholism, drug use, as well as the descriptions of occupations. I then used the fuzzy match and k-means clustering analysis to sort the applications into different medical condition groups, as well as occupational classes, so I can create dummy variables and categorical variables in step 2. Step 3 is to use preliminary data analysis to gain early insights into data, as well as to decide on the appropriate treatment for missing data. Step 4 is to use independent feature selection method to eliminate variables. The key word here is independent, meaning the feature selection methods themselves do not depend on the underlying machine learning algorithm. So the variables eliminated at this stage includes variables with uni-values, so they have no predictive power, and variables with high correlations with the preceding variables, so they are regarded as redundant. The fifth step is to use dependent feature selection method. This is very similar to the fourth step, except the methods themselves do depend on the machine learning algorithm, so I need to specify the algorithm before I can use the feature selection method. This also means that step 5 is essentially embedded into step 6, which is model training and fine-tuning of parameters. This table here shows how the outcome variable underwriting decision is coded. So the standard case is coded as 0. the decline cases is coded as 100. In practice, the underwriters for this data set only give out loadings in multiples of 25%. So the models are designed to follow this practice, and therefore the loadings are divided by 25% and coded as shown in the table. In practice, underwriters rarely give out loadings greater than 400%, so I grouped all the cases with extremely large loadings into one risk class and labeled this class as 20. In the end, there are 19 classes in total. So this table here shows the model performances of different machine learning algorithms that are tested, as well as the performance of more traditional generalized linear regression model. The dataset is split into training dataset and testing dataset in the ratio of 80% to 20% randomly. As you can see, the best performing model, Extreme Gradient Booster, achieved 100% accuracy score on the training dataset and 80% accuracy on the testing dataset. So the training dataset is used to train the model, and the testing dataset is used to test the model performance on unseen data. So the more meaningful score here is the 80% accuracy achieved on the testing dataset, because once your model is constructed, not only you want to see how well it fits the past data retrospectively, you also want to see how it fits the unseen future data, because they don't come with a decision label. Now, 80% accuracy score may not sound that impressive initially, but if you think about it, it's achieved for a 19-class classification as opposed to binary classification problem. So this means that model is not only able to predict accept a / decline decision, but also the underwriting loading to apply should a case be accepted. So, for example, if the model predicts the underwriting loading to be 100% and the actual loading is 125%, the prediction will be counted as an incorrect prediction when we calculate the accuracy score. However, in practice, the distinction between adjacent underwriting loading classes are not exact science. And so the cost of having 100% underwriting loading versus 125% underwriting loading may not be material at all. And to put this number to put the above accuracy into numbers, of 11,029 data points that we used to train the models, the best performing model achieved 10,544 correct predictions, which is represented by the green bar. As you can see, it completely dwarfs the other two bars, which represent the incorrect or failed predictions. So if we enlarge the two almost invisible bars, we get the graph on your right-hand side. That is, to further split the 508 failed predictions into 416 incorrect loadings versus 92 incorrect underwriting decisions, which translates into 0.8%. That is less than 1% of the entire data set. Next, we will look at the distribution of differences between the predicted and actual labels. So a quick recap, the labels are 0, 1, 2, 3, all the way up to 16, then it's 20, then it's 100. And if we calculate the differences between the prediction and actual labels, only for failed predictions, because they are the cases that have differences between the predict and actual. And then we count the policy counts for each difference label, we get this histogram or distribution graph. To use the consistent color coding as the previous slides, the red bars represents the incorrect underwriting decisions, and the yellow bars represent incorrect underwriting loadings. As you can see, majority of the failed predictions are concentrated in the middle. To give you a better idea, 47%, that is almost half of the failed predictions, are small differences between the prediction and actual loading, and the differences being between -2 and 2. And 2/3 of the failed predictions are differences between -4 and 4. So this diagram gives us the comfort that when a model makes a failed prediction, it's more likely to be incorrect loading as opposed to incorrect underwriting decision. And the differences between the predicted and actual loading tend to be very small. So the financial impact of a failed prediction is unlikely to be material. Another useful analysis is to look at the prediction breakdown by risk class. So if we take the 80% overall accuracy score achieved on the testing data set and break it down by risk class, we get this table, which shows the prediction accuracy as well as the number of cases for each risk class. As you can see, for standard case, the prediction accuracy is 92%. For cases with extreme large loadings, you get almost 90, sorry, I'm trying to use the laser there, 90%. And for decline classes, it's 72.5% accuracy. So the financial impact of having a failed prediction for a decline class could potentially be high. So we will come back to look at a couple of examples for this class. Other classes with higher or lower prediction accuracies tend to be smaller classes with insufficient data points for the models to train. So they are almost negligible. To put this into practical terms, if we were to implement extreme gradient boost to predict underwriting decision for refit cases, and the model predicts a case to be a standard case, 92% chance that this is the correct underwriting decision. So let's look at a couple of examples of failed predictions. Policy 1 is a 72-year-old retiree with a BMI of 26 that is medically defined as overweight. Policy 2 is occupational class 3, aged 33, with a healthy BMI of 20. The two cases are otherwise identical. Both are term insurance with sum insured less than 1 million. Both applicants are female. Neither has any medical conditions nor family history of any conditions. Neither has any lifestyle risk factors such as alcoholism or drug use. The first policy is accepted on standard term by insurer X. The second policy is declined by insurer M. The model predicts the first case to be declined because of old age and high BMI. The model predicts the second case to be a standard case because of young age, healthy BMI, and lack of medical condition. If you think about it, the model predictions actually make more sense. One possible explanation is that insurer X might have a different underwriting practice to the rest of the market. For example, it's focusing on a specific niche market, or it's linear at underwriting stage and more strict at the claim stage. Insurer M might have declined the case based on information that's not recorded in the data. So what we often see in practice is that, for example, all the applicants with diabetes conditions will be recorded as diabetes. Some applicants have taken active steps to manage their blood sugar levels, so they have almost similar vital numbers to those of a healthy individual, so they can be accepted, whereas other applicants do not take active steps to manage their blood sugar levels, so they tend to be declined. Now, this extra detailed information are available to underwriters through phone calls or follow-up questionnaires or GP reports, but they're not recorded in the data. So there's no way for the model to distinguish between two kinds of applicants. So the model predicts the same underwriting decisions for all applicants. This is where one of the areas that improvements in data quality can further improve the model prediction. What this means is that a failed model prediction may not necessarily be a bad thing. It can help us to highlight the areas of inconsistent underwriting decision making, as well as the areas where we can make further improvements in data quality and in turn improve the model prediction. This graph here shows the model performance against the number of features selected. As you can see, the model performance increases sharply with the top 40 most important features selected, and therefore, thereafter, it pretty much flattens. In the end, 125 features were required to maximize the model performance, but the incremental increase in model performance is almost negligible after the top 40 features were selected. This means that if insurers want to design a compact version of their application form to speed up the process, they can do so, and it would benefit by capturing the top 40 features as accurately as possible. So the next question is, what are the most important features? The best performing model, extreme gradient boost, has a feature ranking function that ranks all the input variables in descending order of information gain. This shows the full ranking of all the input variables. It is too small for you to see, so if we only show the top 60 most important features according to the model, you get the graph on your right-hand side. As you can see, the most important feature is no condition indicator, which equals to 1 when the applicant has no condition and 0 otherwise. This is obvious since applicants with no medical conditions tend to be accepted on standard terms. The second most important indicator is insurer X, which suggests that insurer X has a different underwriting practice to the rest of the market. This is consistent to what we saw in the previous slide. You also notice that all the indicators indicating product lines are ranked pretty high, namely mortality, IP, PHI. This suggests that we tend to make different underwriting decisions for different product lines. We'll come back to this point in the next slide. Important medical conditions include diabetes, heart, lung, liver, as well as psychiatric conditions. You will notice, or maybe surprised, that you won't see cancer on those top 60 features. This is because applicants with cancer conditions tend to get declined very quickly without ever being referred to reinsurers. One interesting observation here is that divorce indicator is very high on the ranking. It immediately follows heart conditions, and it is ranked higher than a lot of medical conditions. It's very interesting for an indicator that relates to neither medical condition nor product risk. So if anyone wants a scientific proof of happy wife, happy life, here it is. So back to the point where I mentioned that we tend to make different underwriting decisions for different product lines. What you see here is a so-called scatter plot matrix. So this is a very useful visualization tool where you can spot patterns in data. For example, mortality and disability indicators are shown in row 3 and 4. And if we enlarge it, you get the graph on your right-hand side. It's almost a mirror image, suggesting that we tend to decline mortality products more than disability products, and we tend to accept disability products on standard terms more than other products. So as a conclusion, you can use machine learning models to predict underwriting decisions, at least for referred cases, with reasonably high prediction accuracy. It achieved 100% on the training data set and 80% on the testing data set. If we further break it down to different risk classes, you get 92% accuracy for standard case, which means if we were to implement extreme gradient boost to predict underwriting decisions for referred cases, and the model predicts a case to be a standard case, 92% chance that this is the correct underwriting decision. We looked at failed predictions and realized that it is more likely to be incorrect loading versus incorrect underwriting decision, which only counts 0.8%, that is less than 1% of the entire data set. We also looked at the distribution of differences between the prediction and actual labels, and see that the differences between the two tend to be small, which gives us the confidence that the financial impact of a failed prediction tend to be immaterial. We also looked at some of the underwriting insights, for example, the number of features required to achieve satisfactory or even maximize the model performance, as well as the most important features and what they mean for underwriting. Last but not least, if you implement the machine learning models to predict underwriting decision, and next time you need to decline a case, you can always blame the model. Thank you. I hope you enjoyed my presentation, and if you have any questions, I'm happy to take it now, and my contact details are on the screen.